Topic 4.4, wave behavior. In this video, we're only covering Snell's law, and so here's the equation. For Snell's law, refractive index of medium 1 divided by the refractive index of medium 2 equals sine theta 2, that is the refracted angle, over sine theta 1, the incident angle. Those angles are with respect to the normal. That's equal to v2, the velocity of the wave in the secondary medium, divided by the initial velocity of the wave. Reflection is the first wave characteristic that we discuss. When waves reflect, this occurs at a boundary. The wave meets a boundary like a solid object or a different medium, like a different type of gas or a different liquid, and it's at least partially diverted backwards. Some of the wave might be transmitted, but the rest of it is reflected back, so we can see this. Here we have an incoming beam or incoming wave, and this would be the incident ray, and then we have the reflected ray, and this is measured with respect to the normal, and the normal is this purple line. It is at a 90-degree angle perpendicular to the surface. Always the angle of incidence equals the angle of reflection. The surface on which a wave reflects determines what happens to the wave after reflection. So we can have a fixed boundary condition, one in which we have a pulse traveling along a string, and when this pulse reaches the end of the string and it hits the boundary, this brick wall, it inverts. This is the fixed boundary condition. Now for light, how would this occur? Let's say I have this boundary. I have air on one side of the boundary and water on the other side of the boundary, and I'm going to draw this dashed line to represent the normal. The normal is 90 degrees perpendicular to the surface, and I have a beam of light coming in. Because water is denser than air, the beam of light that gets reflected off of the surface undergoes a 180-degree phase shift. So it's going to reflect off, but the phase, it's now out of phase with itself. And remember, these two angles are identical. The angle of reflection the angle of incidence equals the angle of reflection. Theta I equals theta R. Now we can have a free boundary condition, and in the free boundary condition you have a wave pulse, for example, traveling along a string, and let's say the string isn't glued down or tacked down to any wall. It's just connected to a rod by a ring, and so if I can send a pulse down, it reflects off of this free boundary without undergoing a phase shift. In the case of light, let's say I have a boundary between water, H2O, and air, and in this case we will have the light is going to be reflecting from underneath the water. So I can have light coming towards the normal here, and when the light reflects off of the boundary from water to air, there is no phase shift. The rays are still in phase, no phase shift. And this occurs because air is like a free boundary compared to water. You will have to know when waves become phase shifted. They become phase shifted at the fixed boundary condition. They do not experience a phase shift at the free boundary condition. So let's look at not just rays but wave fronts. Observe. We have a series of wave fronts, and they are reflecting off of some reflective surface. We can draw these as spherical wave fronts on the left or flat wave fronts on the right. And it's important, you must know that during reflection, the frequency and the wavelength of the wave do not change. Only the phase of the wave changes depending on the boundary condition. Frequency doesn't change, wavelength doesn't change. So we'll be getting into refraction, and as we do, it might be helpful to think of a metaphor. So imagine we have ranks of a marching band. So we have these people, and they're all lined up, and they're marching forward, playing their instruments, and they're marching across concrete. And then there's a boundary change. They're going from concrete into deep mud. And as they do, you can see how the lines of people get closer together into the deep mud. So the cadence doesn't change. They're still marching in formation, in rhythm, but the period, so that means that the frequency and the period also do not change. But the speed and the wavelength do change. They're going to go slower in the deep mud, and the ranks of people are going to get closer together. They bunch up. If the frequency of a wave changes, especially, well, the frequency of a light wave changes, the energy changes. So frequency does not change through different media, but the wave speed and the wavelength do, and frequency is conserved. So wave refraction is the second type of wave behavior that distinguishes waves from particles. We have reflection and now refraction. And refraction occurs when a wave meets a boundary, like a solid object or a different type of liquid, and it's at least partially allowed to pass through that boundary. And as it does, the wave changes direction. So let's say we have clear water on the left and muddy water on the right. So muddy water is denser than clear water. So we have waves that are going to be passing through this boundary. These are the wave fronts, and you can see that after the wave fronts have passed through the muddy water, the direction of the wave fronts have changed. The spacing between each wave front has also changed. They've gotten closer together in this example because muddy water is denser. Along the boundary is where this change occurs. So we have the incident wave, these are the wave fronts, the refractive wave fronts in a different direction, and we can represent all of these wave fronts using this perpendicular ray. These are the two arrows that are drawn. And notice that we have this dashed line going through the middle, going perpendicular to the boundary. This is the normal line. The normal line is always drawn at a 90-degree angle perpendicular to the boundary. This is how you measure the incident angle and the refracted angle. So the angle of incidence is always measured with respect to the normal line between the ray and the normal line, and again the angle of refraction is always measured between the normal line and the ray itself. So some students will try to measure between the boundary. No, it's not the angle between the boundary and the ray, it's between the normal and the ray. Without derivation or discussion of Fermat's principle, I present Snell's law, and this relates the wave's velocity in the two different mediums with the angles of the wave fronts with respect to the normal. Practice 1. A wave traveling at 50 meters per second strikes a boundary as shown. Part of the wave energy is reflected and part is refracted. What is the angle of reflection? So check out this diagram right here. And you can see what's going on. We have this ray that's incoming to this boundary. The boundary is right here, separating the two different media. And we see that the refracted ray, the ray that's allowed to pass, is drawn, but the reflected ray is not drawn. So I'm going to go ahead and draw that. Okay, so that's the reflected ray. So you can imagine some of it passes through the second boundary, or through the medium, through the boundary, and some of the ray gets reflected off the boundary surface. And I can see that the angle is measured between the boundary and the ray itself. So the angle is like 68 degrees up there, 75 degrees down here. So in order to correctly measure the angles, you have to measure with respect to the normal. So between here and here. So we will start by getting the angle of incidence. So normal is 90 degrees with respect to the surface. So the angle of incidence, theta sub I, is equal to 90 degrees minus 68 degrees. And that is, 22 degrees. So what is the angle of reflection? Remember the relationship between the angle of incidence and the angle of reflection. So what is the speed of the transmitted wave? So we need to define what the media are. Media 1 is on the left. That's where the incident ray is coming. Media number 2 is on the right. It's the gray shaded region, and this is where the ray has passed on through. It's been refracted. And we need the angle of refraction. This will be our theta 2, theta sub 2, and that is 15 degrees because 90 minus 75 is 15 degrees. And we have theta sub 1, that equals 22 degrees. That's the angle of incidence. The angle of refraction is theta 2. And we can find out the speed of the wave by doing V2 over V1 equals sine theta 2 over sine theta sub 1. Set this up, solve for V2, and hopefully you'll get the right answer. Be sure that your calculator is in degree mode. So a refractive index is used when dealing with light waves, and it describes the speed. It's a ratio of the speed of light in a vacuum over the speed of light in some medium. For example, that medium can be glass or a diamond or water, oil, whatever. So it shows this relationship between what the speed of light normally would be in a totally rare or non-dense medium to a denser medium. So the index of refraction, N sub m, is equal to c, where c is the speed of light in a vacuum, divided by the velocity of light inside of some medium. And it is related to Snell's law. N1 sine theta 1 equals N2 sine theta 2, where N1 is the index of refraction in the initial medium, and N2 is the index of refraction in the secondary medium. So practice number 2, light enters a glass sample and is refracted as shown, in the figure. So up here, we're going to use this figure. Okay. What is the index of refraction of the glass sample? So to do this, we are going to use this equation. N1 sine theta 1 equals N2 sine theta 2. Are these angles as provided measured correctly? And yes, they are. 40 degrees is theta sub 1, 36 degrees is theta sub 2. Air has an index of refraction, N sub air, which happens to be N sub 1, is equal to 1.00. It's about 1. It's almost the same as in a vacuum. We are looking for the index of refraction in glass, N sub 2, unknown. So we will plug in the values into the equation. N1 is 1, sine 40 degrees equals our unknown N2, sine 36 degrees. If your calculator is in degree mode, you should be able to solve for this. And then once you solve for N2, what is the speed of light in the glass sample? The speed of light in air is 3e8 meters per second. So then you'll use this equation right here. N sub 2, in this case, equals the speed of light divided by V sub n, and solve for V sub n. It's very important. When light enters from a low index of refraction to a high index of refraction, it is refracted towards the norm, as evidenced up here. This angle got smaller because glass has a higher index of refraction than air. When light enters from high to low, it is refracted away from the norm. Imagine that the light beam tries to take the shortest path through the material, which would be right along the normal of the material. Anytime light travels into a thicker medium, a denser medium, it is refracted towards the norm. Practice 3. A light ray passes from air to water as shown. When the ray passes into water, A, what happens to the angle of the ray as it passes into water? Remember that air is a less dense medium than water. B, what happens to its frequency? C, what happens to its speed? And then D, what happens to its wavelength? Now, if the speed decreases, speed of the wave is equal to frequency times lambda. Speed is decreasing. Frequency does not change. What happens to the wavelength? A series of waves pass from deep water to shallow water. What happens to the speed of these waves? Think about it. Deep water is denser. Shallow water, less dense. So for those of you who enjoy really fast internet, we have finally total internal reflection. When a wave moving in an optically dense region arrives at a boundary with a less dense medium, it is possible to have all of the light reflected back into the dense medium. thereby trapping it inside. This is the principle behind fiber optic cables. So the critical angle is that incident angle, theta sub c, at which the angle of refraction is 90 degrees. So we've dealt with rays that are passing into some boundary. Let's say this is air and this is water. And I have a beam of light traveling towards air. And it can reflect at the boundary, but it can also be refracted through. What if there was a special angle that could force that refracted ray down to be 90 degrees at the boundary? This is the critical angle. At this angle, none of that light passes through the boundary. It all just internally reflects. Notice that my N1 is greater than N2. This is the result, because sine of 90 is 1. That sine theta sub c equals N2, the medium of the lower index of refraction, divided by N1, which is the higher index of refraction. And this is Snell's law for critical angles. You can see total internal reflection here in this GIF. We have propylene glycol, 1.43, the surrounding air, 1.00, and the laser beam that's traveling through the bucket out of the opening, it stays inside of the propylene glycol. That's the principle behind total internal reflection.